Okay guys, in this next video we're going to start talking about electrochemical cells. And so there'll be some different types of notation that we'll learn about, as well as a diagram I'll be referring to. I'm going to start off with the broader term of an electrochemical cell. It's a system of electrodes, often metals, although not necessarily only metal, and electrolyte solutions. Okay, so the electrodes are typically dipped into the electrolyte solutions. And a chemical reaction is used to either generate electricity, or an external power source is used to drive a reaction. And so there are two broad classes of electrochemical cells: Voltaic cells, which are also called galvanic cells, are a type of electrochemical cell where a spontaneous reaction is used to generate electricity. And so this would be a battery. All chemical batteries are examples of voltaic cells. On the other hand, you can also have an electrolytic cell. This is where an external power source is used to drive a non-spontaneous reaction. We are going to focus the bulk of our attention in this chapter on voltaic cells, but in the last section we will discuss electrolytic cells. So the rest of this lecture focuses on voltaic cells. As I said before, they employ a spontaneous redox reaction to generate electrical energy. And so here's an example of a redox reaction. You've got copper metal reacting with silver ion. The copper is oxidized, so the copper gives up electrons. Those electrons are given to the silver plus, which is then reduced to metallic silver. Down below here I've written the two half reactions for this redox process. And the idea of a voltaic cell is to physically separate the two half reactions from one another. Okay, and so the two half reactions take place in what are called half cells that are isolated from one another. They are connected via wires and a salt bridge, as we'll see in the diagram, which allows electrical current to flow through the circuit. And you can put something in between the two half cells and use that to drive a device. If this reaction were spontaneous, that is, if electrons will spontaneously flow through the circuit, then you can use that electrical current to do work. Okay, so here's just some rules for how voltaic cells work. Oxidation reactions occur at the electrode that is called the anode. Okay, so here's what I like to remember. Oxidation occurs at the anode. And you just say that to yourself over and over again until it sticks. Because the anode produces electrons, it has a negative charge. So it's the negative pole of the battery. Reduction, on the other hand, occurs at the cathode, where electrons are consumed, and it takes on a positive charge. We use a salt bridge to allow ions to flow between the two half cells. This completes the circuit and allows charge to move through the circuit. Anions migrate towards the anode. That's why it's called the anode. Cations migrate towards the cathode. And so let's look at the picture here to explain this idea. So it's the same reaction that we were looking at before, where copper is oxidized and silver is reduced. So we have a piece of copper forming our anode and a piece of silver which forms the cathode. Okay, as the reaction occurs, okay, copper atoms within the electrode give up their electrons, and then the copper ions then move into the solution. The electrons then travel from the anode to the cathode, where they encounter silver plus ions, which are then deposited as metallic silver. So you've got electrons flowing from the anode to the cathode. Now you need to have current flowing across the other side of the circuit as well, and that's the purpose of this so-called salt bridge. Okay, it's a plastic tube typically with a type of gel in it, and then the gel has dissolved ions. So something like sodium nitrate. In this case, these ions provide for the flow of charge around the backside of the circuit. So the anions in the salt bridge migrate towards the anode, and then the cations migrate towards the cathode. Depending upon the energetics, the thermodynamics of the redox reaction, you will get a particular reading in terms of the voltage of the electrochemical cell. Now we'll talk more about cell potentials in the next video, but I just wanted to point out that's going to be an important part of what we discuss. We use a particular notation called cell notation to represent electrochemical cells, so it's a shorthand. And here is an example at the top here of cell notation for a particular electrochemical cell. And so on the left-hand side represents the anode. Okay, so you have a zinc metal anode, and then the vertical line denotes a phase boundary, and so this would be the phase boundary between the solid electrode and the aqueous zinc ion solution. And you can read this cell notation from left to right, and then write down the corresponding half reaction that it represents. So you go from zinc solid to zinc 2+, and that's going to require giving up 2 electrons from the zinc. Okay, so this is the half reaction corresponding to this anode cell notation. The double vertical bar denotes the salt bridge in the electrochemical cell. And then on the right-hand side of the salt bridge, we have the cell notation for the cathode. And you can read it from left to right. You've got copper 2 being reduced to copper, and that's going to involve 2 electrons for that half reaction as well. And of course, as we've learned in the previous videos, you can combine the 2 balanced half reactions to give the overall cell reaction for this electrochemical cell. So again, double bar indicates a salt bridge, a single vertical bar indicates a phase boundary. In some cases, you'll see a comma is used. That's where the components of a given electrode are in the same phase. And we'll see some examples of that. Very frequently, the conditions of the electrolytes in the solution or in the electrochemical cell are given. So it's not uncommon to see this type of notation where it implies that the zinc ions have a concentration of 1 molar in the anode. Here in this cathode, you're using H+ at a concentration of 1 molar. And this particular cathode is called the hydrogen electrode, and I think I have a separate slide on that as well. So, okay, so what we need to be able to do is convert from redox reactions to cell notation and back. Okay, so given this redox reaction, what are the half reactions of interest, and then what's the cell notation for the electrochemical cell? So what you need to do in order to assign the half reactions, you have to look at the oxidation numbers. So we have elemental chromium, so that's an oxidation state of 0. Here we have copper in the +2 oxidation state. Sorry, I don't know if I said chromium or not. Anyway, this is chromium oxidation state of 0, copper 2+ oxidation state. On the other side of the reaction, we have chromium in a +3 oxidation state. So we can see that the chromium is oxidized and that the copper is reduced. And the rule is oxidation occurs at the anode. Okay, so we'll have the chromium being oxidized at the anode. That'll involve giving up 3 electrons. The copper is reduced at the cathode, so copper +2 electrons gives us metallic copper. what would be the cell notation for this? Well, we read the half reactions left to right and write down the notation as we go. So you're going to have chromium, and then there's going to be a phase transition between, or a phase difference rather, between the chromium and the chromium 3 plus in the electrochemical cell. So there's a vertical bar. Then we have the salt bridge, and then we'll start with the notation for the cathode. We've got the copper 2 plus, a phase boundary between the electrolyte solution and the metallic electrode. And so that's our cell notation for this particular redox reaction. Here we're being asked to consider a cell where copper 2 ions are reduced to copper metal and zinc metal is oxidized to zinc ions. Oxidation occurs at the anode, so zinc goes to zinc 2 plus. Reduction occurs at the cathode, so the copper 2 gets reduced down to copper. For the notation, it's zinc, then there's going to be a phase boundary, then you'll have the zinc 2 plus. Then you've got the salt bridge. You can then start on the cathode. You've got the copper 2 plus, a phase boundary, and then the copper. Here, we're doing the opposite. We are given the cell notation and being asked to write the cell reaction. So the anode is on the left, and the anode is where oxidation occurs. So in this case, you're going to have thallium going to thallium plus. That's going to require giving up 1 electron. For the cathode, you've got the tin 2 ions. They are being reduced to tin, involving 2 electrons. In order to write down the overall cell reaction, you need to take this first reaction, multiply it by 2, and then add it to that one so that the electrons cancel. And this is the result. For the part B here, we have a reaction where at the anode, zinc is being oxidized to zinc 2 plus. And then at the cathode, I'm missing a comma here between these 2 irons. The comma is used when components of the electrode are in the same phase. In this case, we have iron 3 is being reduced to iron 2. And so here is the half reaction. And then this is occurring at a platinum surface. So the redox reaction, both parts of the half reaction are in the same phase, but it occurs at a platinum metal surface, and so the platinum serves as the electrode, but it's not involved in the electron. It's not involved in the reaction, other than providing surface sites for the reaction to occur. And so that's written above the arrow typically. In order to balance this reaction, you need to multiply this reaction by 2 and then add it to that one. And it gives us this is the balanced redox reaction for that particular cell notation. I'll leave part C as an exercise for you guys to try. And I'm going to go ahead and stop this video right here.